All right, continuing on with 9.1. Okay, so we'll look at another example of this. Now this, I've been waiting to come across this example because I knew this example was coming up in our notes. And this is probably not a very sensitive example to be giving, considering what we're going through right now with coronavirus. Or I should have changed it from bird flu to coronavirus or something. No, that would have been too on the nose, right? A little too close to home, maybe. But anyway, I knew that this example was in here, but the problem is I wrote these notes, I posted them at the beginning of the semester before I knew, of course, that like this craziness was going to happen. And now at this point, it's too late to change it because you all have printed the notes already. Anyway, so here we go. Bird flu. Okay, it was a big deal a few years ago. Anyway, as a potential worldwide pandemic, avian influenza H5N1 poses a serious health risk, or used to, right? As of January 24th, 2012, there have been 583 cases of this virus in the world. Of these, 344 resulted in death. So it maybe didn't spread quite as much as coronavirus, but I think it was a little bit more serious. Like you were more likely to die from it if you did actually end up getting it, right? Anyway, part A says, find a point estimate for the proportion of people who would die if infected with the bird flu. So this is just a review of what we talked about like on the first page, right? The point estimate is just the sample proportion, p.5, right? So that would be 344 out of 583. That comes out to about 59%. Okay, so over half of people. Okay. Now part B says, construct and interpret a 99% confidence interval for the proportion of cases that would be expected to result in death if a pandemic occurred. Okay, so if this were to spread worldwide and everyone got infected, what proportion of the population would we expect to pass away from it? We want a 99% confidence interval. So let's do this in StatCrunch. We're going to go to Stat, Proportion Stats, Proportion Stats. I can't spell. One sample with summary. They're going to prompt us for the number of successes. In this case, we're considering death to be success, right? So we're saying 344 people were successful. 344 people passed away. So X number of successes, N was the number of trials, that would be 583, right? So they're going to prompt us for the number of successes, number of trials, and they're going to prompt us for the confidence level. In this case, we want a 99% confidence interval. So our confidence level is 99%. Okay, let's go to StatCrunch and see what we get. Okay, so stat, proportion stats, one sample with summary. We had 344 deaths out of 583 infections. We want a 99% confidence interval. Okay. There we go. There's our sample proportion. It's the same as what we computed in part A, right? About 59%. Okay. And here's our confidence interval for the population proportion. So based on a sample proportion of 59%, we are 99% sure that somewhere between 53.6% and 64.3% of people would die if they were infected with H5N1. So we can write that down as our answer. So our interval is, if we round it to 3 decimal places, 0.538 and 0.643. There's the interval. As far as an interpretation is concerned, you could say we are 99% confident that somewhere between 53.8% and 64.3% of people would die if infected with the bird flu. Okay. Okay. So that's that. Kind of a brutal example, right, given what's happening in the world right now. But anyway, so that's that one. There is one more topic in this section that I want to cover, and it has to do with figuring out the sample size that you need in order to estimate a parameter. Okay, in particular, in this section, in order to estimate a proportion. Sorry. Okay, so recall the margin of error is given by this formula here, right? It's the critical value times the standard deviation. The standard deviation is just square root of p hat times q hat over n. Says what happens to the margin of error as the sample size n increases? Well, as n increases, right, everything else stays fixed, right? So as n increases, this fraction gets smaller. We've talked about this fact many, many times this semester, but again, right, if you have like a 1 in the numerator and like a 10 in the denominator, if the 10 increases to a 100, then you're comparing 1/10 to 1/100th, right? 1/100th is smaller than 1/10, right? And 1/10,000th is smaller than 1/100th, and 1/10,000,000th is smaller than 1/10,000th, right? So as n gets large, our margin of error gets small. So as the confidence level increases, so does the margin of error, right? If we want to be more confident that our interval contains the true population proportion, then we need to make the margin of error larger, okay, to contain more numbers. But as our sample size n increases, the margin of error decreases. Okay? So these two things taken together allow us to determine how large our sample needs to be before we collect data. So we take this formula here and we call it E, right? We say E is z sub alpha over 2 times square root of p hat times q hat over n. And if you take this equation now and solve it for n, then you end up with the results that we're going to look at on the next page.